Hi, everybody. Welcome back to Chem 161. What an interesting day on the internet, particularly if you are a hedge fund investor. What do we got going on today? Oh, I didn't edit the... Hold on. Let's just get rid of this. So we're not starting chapter 2. We are continuing chapter 6. What do we got going? So lab worksheet number 2 is due Tuesday, and so is quiz number 2. I didn't update this, and there we go. Yeah, I just went to check it out because, like, hey, if there's a get-rich-quick scheme, like, I'll throw $100 at it. But there's so many people involved in it that now it's just overwhelming, and I'm just like... I figure the best that could happen would be that I could just double my money, which is cool and all, but I don't really have that much money to throw around, so... Like, if it was $100 and I could turn it into 10,000, then sure. But turning 100 into, like, 250... not as appealing, so I'm kind of just content to watch this play out and watch it all burn. It's kind of amazing. If you haven't heard the news about what happened, there are specific stocks that have been doing very poorly for a long time. So one of them is GameStop. Everybody knows what GameStop is, and it's kind of a joke, right? Like, you take all of your games to GameStop, and then you get, like, 74 cents for it, and then you can only apply that to a PS5 or whatever. Well, what some people decided was, I see that people are short-selling GameStop stock. And what that means is that, basically, they're betting on the fact that it's going to go down in value so they can make money on that. So the Redditors said... okay, well, what if we inflate the value of the stock by just mass purchasing it? We'll all get our money together and we'll all just buy stocks. And so they did, and then the value goes up a lot. And then the people who were short selling because they were borrowing stock so that they could then sell it when it costs less and then keep the money are now out literally billions of dollars. And it's kind of wonderful because it just goes to show you that all of Wall Street and like economy is just like it's a construct. So like money is a construct, and the fact that you could snap your fingers and do something like this and make all of this money just move wherever you want it to. These people have been doing this for so long, and people think like, oh well, no, it's totally okay. Yeah, the economy's doing great. Look at the Dow. It's all bullshit. Like people are just trying to play you. Like, and you can play against them by their rules and steal their money, rightfully so. So like this is the ultimate like Robin Hood chaotic good fantasy, and I just loving watching it play out. It's so good. All right. That was let's talk about stocks. Let's talk instead about empirical formulas and start with this practice problem. We were here yesterday. We did these problems on the that you see on the screen right now. So what I want you to do is take what we learned yesterday about empirical formulas. Remember, turn all the masses you have into moles. Take those moles, make the pseudo formula, and then divide by the smallest number to get the actual formula. And do that here. Okay, so the first problem I just give you some masses, so that's straightforward. The second problem I give you an elemental analysis, and so it has a percentage of carbon and oxygen. If you are given an elemental analysis, the trick to these sorts of problems is to realize that, okay, any sample that I pick will be 27.29% percent carbon and 72.71% oxygen, whether it's like 1 gram or 1,000 grams or 74,802 grams, whatever. So pick an easy number, like 100 grams, because 27.29% of 100 is 27.29, right? So now you know the mass is right off the bat, despite it being hidden, quote unquote, in these percentages. So try these two problems. And I hope if you are investing that I hope you make money. Then you won't need this class anymore. Let me know if you need to drop because you are a millionaire, and then I don't know, send some my way. No, don't do that. I cannot actually take bribes. Hear that? Any administrators listening? I'm not actually asking for a bribe. That would be unethical. I actually love my job. I would keep doing this even if I won the lottery, believe it or not. Mostly because if I didn't have this job, what would I do? I'd be so bored. All right, anyway, find the empirical formulas for these two problems, and then we'll go over the answers in 6 or so minutes or so. That's probably long enough. So good luck. And if you have any questions, let me know in the chat. All right, another minute or so, and we'll go over the answers here. All right, let's go over here. Uh-oh, I moved the wrong thing there. Hold on. It is so hot in my office. Why? I don't know. It's hot in my room here, but oops, what did I just do? Ah, I don't want to go over there. I have the heater on, but it's set to low, and it shouldn't be this hot. I need to rotate this pad of paper real quick. There we go. Okay, so we have this many grams of iron, and we have this many grams of oxygen. So the first step is to turn everything into moles. So let's do that. So we'll do grams of iron, moles of iron. I literally just looked this up and I forgot the number. 55.845. Okay. And this should still be in my calculator because I did this problem already. 0.4527 moles of iron in the sample. We'll do the same thing down here. And this is 15.999. When I type that in the calculator, oh, I did 16. I'm going to get a very similar number, but we'll just 0.6794. Oh, it's the same number. Oh, look at that. Not enough to change it. Okay. So there's our results. So now what we're going to do is we're going to make the pseudo formula. So Fe 0.4527 O 0.6794. It's not any formula I've ever seen, so what we're going to do is we are going to divide by the smaller of the two numbers. Let's try that line again. Oop, that's better. And when I do that, I get Fe is just 1 because it's divided by its own number. And then for O, I got 1.5005. So that's really close to this. Okay. Remember what we said about fractions? If something looks like a fraction, and this number right here looks a lot like this fraction, right? 1.5 or 3/2. So I'm going to times these by 2 to get the empirical formula. that only has integers for my atoms. And there you go. So this is just iron 3 oxide. This is rust. All right, this next one, I tell you it's a gaseous compound. That doesn't really mean much, but if you get the formula of something and it's also gaseous, like that could tell you something. So let's scroll on down here. We're going to do the same thing, but this time we have a percent for each one. And remember, in a 100-gram sample, if I had exactly 100 grams, I would then have 27.29 grams of carbon and 72.71 grams of oxygen. So we're going to treat it exactly the same way. We're going to turn it into moles. This one I didn't do, so I got to calculate it. 27.29, 12.011, 2.272 moles of carbon. We're going to do the same thing down here with oxygen. $72.71, 15.999, enter. 4.545. Okay, let's make a pseudo formula. And then divide by the smaller number. And so I get C is just 1, and I'm going to suspect that this is going to be a 2. But I'm actually going to do the calculation. 2.000. There you go. That's the formula. And hey, that is a gas, so that checks out, right? Sweet. So there we go. We can do empirical formulas. Now, it's not necessarily true. Sorry, hold on. My back itches, and I can barely reach it. There, that's better. It's not necessarily true that this molecule is the empirical formula that we're given. Because remember, an empirical formula is just the ratio of the atoms to one another. So this could be CO2, but it could also be like C2O4 or C3O6 or something like that. As long as the ratio is 1 to 2, our molecule could have that formula. So now what we're going to do is we're going to add to this topic, we're going to show how to get a molecular formula. And the way that we do that is we use mass spec. So we would do the exact same process that we did here, but then we would feed our sample into a mass spectrometer to learn what its molar mass is. And that would tell us something. So first of all, let's talk about the empirical mass. So the empirical formula that we calculated will have a mass. For example, we got CO2 in the previous example. Its empirical mass would be 44.01 grams per mole, or whatever. And you just get that by calculating it from the periodic table or LenTech. For an actual molecule fed through the mass spectrometer, you will get its molecular mass. Generally speaking, you will have both this information available. I will tell you its molecular mass, and you can calculate the empirical mass because you can calculate the empirical formula. If you take the relationship between these two, you'll get a multiplier, n. So divide my molecular mass divided by the empirical mass, you'll get a whole number. And what that number tells you is, okay, I multiply all the coefficients in the empirical mass by the multiplier, n, to get the molecular mass. And that will give you the actual formula of the thing that you put into the container, or into the mass spec. So let's do an example. Let's suppose that I asked you to solve for the empirical formula, and you got this. You got CH2O. Then you feed your molecule into the mass spec, and it spits out this number. Hey, what you gave me weighs 180 AMU. what did you actually put in there? So let's show how you calculate that. So first we need to know what the empirical mass of CH2O is. And so we would go to Lentech. I don't actually have Lentech up on the board here. Let me grab that. Sorry, I'm chewing on my stylus. There we go. And then I can capture the window. Huzzah. Okay. So we'll just type in CH2O. And you can't see it because it scrolled off the screen. So CH2O weighs 30.03. Okay, cool. Let's go write that down. 30, where's my pen? There it is, 30.03 AMU. Okay. The molecular mass is 180. So what I'm going to do is I'm going to say molecular mass divided by empirical mass equals the multiplier N, which would be 180 AMU over 30.03 AMU. So the multiplier here would be 180 divided by 30, which should be 6. 30, 60, 90, 180. Okay, yeah. So I'm going to take my formula, CH2O, and I'm going to multiply each of the coefficients, so the oxygen, the hydrogen, and the carbon, by 6. And so this is the molecular formula. So this is what you actually put into the spectroscopy. Or spectrometer, actually. Now, that's an important distinction to make because this right here, C6H12O6, this is glucose. This up here, the formula is actually for formaldehyde. One of those is good for you, the other not so much. So, knowing what the molecule actually is in the mass spec could be relevant. All right, I'm going to hit clear because it's going to put all my answers on the board here. Here's another problem that's a little more difficult. And I want you to think about it for just a bit. So here's the percent composition. And then I want you to tell me the molecular formula if a 0.2500 mole sample weighs 40.57 grams. How the heck does that information help you? First of all, start with this first part up here. So use this information to figure out the empirical formula of nicotine, and then see if you can get the molecular formula from the information below it that I'm going to color in a different color. We'll color it in blue. So do the yellow part first, and print the empirical formula into the chat when you get it. And then we'll talk about what to do with the blue stuff in just a second. Okay? So go ahead and work on that. I'll give you a few minutes. Formaldehyde will preserve you. Yeah, I don't need to be preserved. I need to live. So once you get any formula, put it in the chat. Just let me know if it's the empirical formula or the molecular formula. All right, one more minute and we'll go over the answer. And that actually looks good. I believe that that's the right formula. All right, let's try this problem. All right, so the percent composition of nicotine, 74.02% carbon. We're going to just convert that directly into a mass here. 8.710 grams of hydrogen from 8.710% hydrogen, and 17.27, that should be 7 grams of nitrogen. So we're going to do the moles thing, so grams of carbon and the moles of carbon. Grab my calculator here. I got 6.163. Okay. We'll do the same thing for hydrogen. You don't need that many sig figs for hydrogen. It's fine. 8.642. And then finally nitrogen. 14,007. I'm doing these from memory, so if I have like a molar mass that's wrong, let me know. 1.233. Oops, hold on. Okay, we'll make a pseudo formula. C 6.163, H 8.462, and 1.233. Nitrogen's the smallest of those three, so we'll do that. And I get, for C, 6.163 divided by that number is 4.998. That's really close to 5. For H, 8.462 over 1.233. I typed the wrong number. I should have gotten closer to 7, I think. Oh, that's why. Thank you. Yeah, now it's almost exactly 7. So 7.008 and then N. So that's the empirical formula. And then to find its mass, we'll go to Lentech. And they say 81.12. I put the calculator on the pad there. That's not where I want it to be. So 81.12 AMU. Oops, actually, let's just write grams per mole here. Okay, so that's the yellow part. Now let's do the blue part. I have a 0.2500 mole sample, and it weighs 40.57 grams. So if I have this many grams and this many moles, I can figure out what its grams per mole is, right? By just doing the division. 162.3 grams per mole. And so that must be the molecular mass. So now I can take this number and that number and find the multiplier. So 162.23. Oops, sorry, hold on. I didn't get to keep that many sig figs. Grams per mole. So that is the molecular mass divided by 81.12 grams per mole, which is the empirical mass. These cancel. And I don't really need to put this in the calculator, but I'm going to do it anyway. I should get 2. 2.0000. Okay, so I'm going to take this formula, and I'm going to times it by 2. There you go. All right, so that is the molecular formula for nicotine. All right, any questions, let me know. All right, I have butane dione here as another example, so go ahead and try this. I've given you the masses, tell me the empirical formula, and then here's its molecular mass. Tell me what its molecular formula is. Okay? We'll do this, I'll give you 5 minutes to do it, we'll go over the answer, and then it'll probably be time for a break. See you in a bit. I see some answers coming in, so we'll do one more minute, and we'll go over the answers together. All right, so, oops, I need some of the information that got hidden here. We'll just keep that on the screen for now. Okay, so let's get the empirical formula. And by now, this should be, like, very straightforward, so you should be able to do these. .323, yeah. And what else we got? 3.512 grams of hydrogen. And that is going to be 3.484. And then oxygen is 18.59. We're all experts at doing grams moles now. 18.59. 1.162. What I'm not an expert at is reading numbers off the calculator. All right, so pseudo formula time. We're going to divide by the smallest number. That's this one right here. And so I get C2H3O. Those look like 2 and 3. I'm going to assume that I did that right. Okay, so that's the empirical formula. And its mass is, according to Lentech, which I have buried on the screen somewhere. Where is it? I closed the window. Look at me being a doof. I still need that. C2H3O. 43.04, which I believe is exactly half of what was listed on here. So this should be like 86 or something. And it totally is. So molecular mass over empirical mass equals N. So we'll take 86.09 AMU, which is the same as grams per mole, divide by 43.04 AMU, and we get 2. So I'm going to times this by 2, C4H6O2. That's butane done. All right. I would say that we have crushed this into a pulp. All right. We're going to take a 10-minute break. Let me know if you have any questions. During that break, go invest in GameStop. So we'll see you in a bit after this. If I could find the right music that I want to play here. Alright, I guess we gotta get back to work. Alright, he's ready for more. Alright, so that was the first half of Chapter 6. This is the back half of Chapter 6, which is the rest, really, of the lab that you're going to be doing. So, let's talk about molarity. Molarity is a very simple concept that has so many applications that we're going to be using molarity all the time in 162, really. You're going to be using it for quite a few labs because there isn't a lot of content in this class that we can have you manipulate with molarity without actually being in the laboratory and making the solutions yourself. So, a lot of the lab content is sort of focused on that sort of stuff, which is kind of an unfortunate disconnect between 161 class content and what we do in the experimental environment. So this section is mostly used for your lab. So this will probably be really relevant to lab discussion from henceforth. So let's go over some of these concepts. So what is a solution? A solution is any mixture that you put 2 or more things into. Almost all the solutions we're going to deal with in this class are aqueous solutions. So what that means is that the solvent is probably water. Well, if it's aqueous, it has to be water. The solute can be anything you want it to be, whatever you put in there. So when you make a solution, you are going to put the solute into the solvent. By definition, the thing that you put less of is the solute. Now, if you put like a gallon of salt into like a tiny beaker of water, you're not going to make a solution, you're going to make a mess. But if you do it the other way around, you put a small amount of salt into a gallon of water, the salt will dissolve and you'll have a solution. You put the solute into the solvent and the result is the solution. The important thing to note here is that the terms are very specific. So in the formulas for molarity, we're going to refer to these parts. We're going to refer to the solute and we're going to refer to the solution, and the solvent is just sort of there. We're going to add as much solvent as we need to get whatever result we want. And we'll talk about that when we talk about making solutions in a second. All right. Some things about solution concentration. If you have a lot of solute, we call it concentrated. If you have less of it, you call it dilute. So these are just relative terms. You can dilute any solution by adding just water. If you add more solvent, the concentration will get reduced. You could think of this as like if you have soda and you drink it and you're like, oh, that's so sweet. And then you put ice in it and then the ice melts and it adds water. And then the soda is less sweet because it's been watered down. That's dilution. You're taking something that's concentrated and then by adding something else to it, that's something being the solvent in this case, there's not as much solute per volume. Here's a picture of that. So if I have a concentrated solution, these little like blobs here, these represent my solute, and then the empty space behind it is the solvent. So those are solute particles like, say, sugar or salt or something like that. Over here, you'll notice that there are very few of them per unit volume relative to the concentrated solution. So again, these are just relative terms. How do we express concentration? We're going to use this formula for molarity, and I believe it should just pop up. There it is. Note the words that are specifically used here. Note that solvent is not included. Okay? So if you put 5 moles of sodium chloride into 100 milliliters of water, you don't get a molarity. You get some other number. You want the liters of the solution because the solute adds to the volume too, right? It doesn't add much because it's a solid and you're adding it to a lot of liquid, but the volume does change slightly, and we want the calculation to be as accurate as possible. So we have to consider that source of error. So to get around that, we've defined molarity as the volume of the solution, which is both parts put together. What that means is that your description of how to prepare a solution has to be very specific. If I wrote the directions, add 5 grams of, I don't know, say whatever this is, sodium phosphate, to 100 mils of water, I have a problem. I can't calculate the molarity of this, so this is no good. Instead, I have to say add 5 grams of sodium phosphate to enough water to get 100 milliliters of solution. And that might feel like semantics, but it's really not. Because remember that this has a volume. So there's some volume which will be incorporated into this result later. So in reality, you're adding more like 99.7 milliliters, and then the rest of the salt takes up the remainder of the volume. You just want the total to be 100 milliliters, and then you can calculate a molarity. All right, let me clear this. And I'm going to have you calculate a molarity because somebody just messaged me and it seems important. So tell me the molarity of this solution based on these numbers. And we'll go over the answer in just a second. All right, and we've already got the answer. So obviously you just divide these two numbers together. So 2 divided by 1.75. I typed in 17.5 because I'm a doof. I didn't click on the screen, so it's not going to write. So moles of solute would be 2 moles calcium chloride divided by 1.75 liters. And the answer I got was 1.14? Yeah, 1.14 moles per liter CaCl2. Now, this unit that right here that I've written is kind of cumbersome. So one thing that you can do to make that a little simpler is instead of writing moles per liter, we can just write a big capital M. So you're going to see this capital M unit written a lot. And what that big M stands for is moles divided by liters. So we're just simplifying. Okay, we don't really measure in moles. You don't go to the scale and put some solid on there and go doot 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 and type in the formula of it for it to tell you moles. That would be a few too many steps to do at the balance, and you can convert to moles yourself. That's very trivial. So typically, we're going to give you expressions in grams, and you're going to have to convert. Now, because molarity is moles per liter, so that's this guy right here. If I take a solution with a given molarity and I multiply it by the volume of that solution that I use, these cancel out, and I get moles of solute that are in that sample. This is particularly useful because now you can say, okay, how much stuff is in here? Generally speaking, I would make a solution for you in the laboratory and then put it in a giant bottle, and I put it in the stock hood. And you'd go over there and you would grab it and you'd read on the bottle, okay, this is 0.9645 moles per liter sodium hydroxide. And you'd write that number down. Then you would take some volume of it, noting how much you took, and then you just multiply the two numbers together to get the number of moles in that sample that you took. So this is particularly convenient for us because now I can just take any aqueous amount of a solution and figure out how many moles are in there, and then do these calculations like we've been doing all along. So for instance, let's suppose I gave you this, 2.8 moles of, or 2.80 moles per liter sodium chloride solution, and you took 300 milliliters of it, or 0.3 liters. How many grams of sodium chloride would be in there? So let's do this one together. That's wrong. I misclicked. Okay. Oh, it is scrolling. It's just scrolling really slow. Okay. So we know that molarity is moles of solute over liters of solution. And I can rearrange that equation to get molarity times volume equals moles. So if I have 2.80 moles NaCl per liter, and I have 0.3 liters, I'll get an answer that is moles NaCl. And that number is 0.84. 0.840 because I have sig figs. Okay. Now, what is the question asking me? Well, it's asking me to get grams, so I got to turn this from moles into grams. Okay. Well, we know how to do that because we were doing the reverse of this like 74 billion times when we were doing empirical formulas, right? So I just look up the molar mass of sodium chloride, and this one I happen to have memorized. And there you go. So that's how much salt is contained in a third of a liter. Not a third of a liter, I'm sorry. 0.3 liters if the molarity is 2.8 moles per liter. That's a lot of salt, isn't it? Now, for reference, I believe, what is the molarity of ocean water? I mean, some of you might be Orca students, so you might actually want to know this. I want to say like ocean water is like 1.2 moles per liter. Let's just look this up really quickly. Concentration of ocean water. Please don't give me something like 35 parts per thousand. Yeah, thanks. Moles per liter. 3.5% salinity. That is not useful either. Molar concentration. There we go. About 0.61. Okay. So I was off by a factor of 2. So this solution that I have made here in this example is far, far, far saltier than the ocean. In fact, it might be bordering on I'm just thinking here. It's not saturated. I don't believe. All right. So I have some molarity questions just so that you can get used to doing the calculations here. So here are here's a KNO3 solution. Tell me its molarity based on these numbers. How much HCl in grams is contained in this solution? And then tell me how much solution I need to get 19.6 grams of solute out of this molarity of vinegar. We didn't do a problem like number 3, but think about the terms, write out the formula, and then solve for the thing that's missing. Okay? We'll go over the answers in about 5 minutes. See you in a bit. All right, 1 or 2 more minutes. We'll go over the answers. All right, let's go over the answers here. Wow, everything is awful. Let's put these two on the screen here. There we go. All right. What is the molarity of this solution? Okay, so first thing we got to do. So I want to do moles over liters. So I'm going to figure out moles first. So I'm going to turn grams of KNO3 into moles of KNO3. So that those cancel out. I have no idea what the molar mass of KNO3 is, but thankfully I have Lencheck. 101.10. That's not Photoshop, that's OBS. 101.10. Is that the right number? I've already forgotten it. Yeah, it's the right number. Okay. Okay, so this right here that I've written down is the number of moles, because that's the unit that's left. Now what I'm going to do is I'm going to divide by the volume in liters. 225.0 milliliters, that's the same as this. I don't need a second decimal point there. What am I doing? You don't have to have this one here. You could just leave it blank if you want. I just wanted to put something there. .581. That's what I got. There you go. Excuse me. All right. That's the first problem. What mass of HCl is contained in half a liter of 14 molar HCl? All the HCl. So we know that molarity times volume equals moles. So we could write down the molarity times the volume, which is half a liter. And so that will give me the number of moles, and then I could do 1 mole HCl, and I believe it's this. That cancels out there. You don't have to do this all in one step. I'm just doing it all in one step because I like to show that the units cancel. 14 times 0.5 times 36.45. 255 grams of HCl. Sweet, there we go. Let's fix this up real quick. All right. What volume of this molarity vinegar contains 19.60 grams of solute? So first I need to do, let's say molarity equals moles over volume. I'm going to solve for volume here, so I'm going to rearrange my formula to be volume equals moles over molarity. So first I need to know the number of moles. So let's calculate that. I need 19.60 grams of solute. I'm just going to write vinegar because I don't want to be bothered to write the formula over and over. So grams of vinegar, moles of vinegar. I don't know the molar mass of vinegar off the top of my head. HCH, oh, it's not typing, hold on. HCH, H22, H3O2. 60.05. I really should have known that one. So 1 mole, 60.05 grams of vinegar. Okay, so this whole thing is my number of moles. And then I'm going to divide by the molarity, which would be the same as doing this. So this would be moles of vinegar per liter. And so those will cancel out. How many moles are there? 0.8214. My 8 got a little cut off there. And so this would be a volume of vinegar. 19.6 over 60.05. That's not 60.05. 8214. So this is my volume in liters. 0.3974. Or 397.4 milliliters. Either of those is fine. I didn't ask you to tell me what the units of volume were, so however you dice it up, how you serve it up, I guess is the expression, would be correct. All right, if you have any questions, let me know. Looks like people... What the hell was that? Looks like people got the right answer. I don't know if that was outside or inside. I heard a big thump. So I immediately go, what did the cats knock over? All right, let's keep going. So the last thing that we're probably going to have time to talk about today is how to make solutions. We're going to talk about dilutions. And you should be totally prepared for everything you need to do in the lab, because the rest of Chapter 6 is just, what are other ways we can do concentration besides molarity? We can do percent, parts per million, etc. So let's talk about how we make a solution and how we dilute the solution. So let's suppose that you were tasked with making your own solution in the lab. You wanted to make a 1 molar solution of NaCl with a 1 liter flask. And we'll just tell you that this 1 mole per liter would be 58.44 grams of NaCl is 1 mole NaCl. So presumably you would need to multiply molarity times volume to get moles. You could turn that into grams, which is straightforward. We've already done that. But now what's the process that you do? Here it is visually. So, excuse me, to make a solution in the lab, you have to follow a specific order of steps, because otherwise you get into that issue where it's like, oh, did I actually add a liter of water, or did I add enough water to make a liter of solution? So you have to do it this way. Step 1 is you're going to add the amount of solid into the container that you need. So here's your solid. It's collecting at the bottom. Step 2 is to then add the water to the container. Now, the proper technique would be that you want to add the water in here to rinse out any of the remaining salt that might have like scraped against the side of the container. You want to make sure you get all the salt. Now, this is probably only going to recover maybe 0.01, 0.02 grams of salt, but every bit counts because you don't want to introduce error into your solution. So you rinse out anything that the salt came into contact with, and that includes the funnel. Make sure that all that gets in there. And hopefully you use less than this much water, because if you didn't, you're in trouble. Then what you're going to do is, once you've rinsed everything out and you've got all of the salt in there with a little bit of water, you're then going to add enough water so that you reach the fill line. I missed the fill line. God damn it. Good enough. You're going to add enough water until you hit that line. And what this should look like, here's your fill line. Your water level needs to touch the fill line so that the meniscus touches the center of the line as close as you can. The line's very thin, so you're probably going to land on the top of it. That's totally fine. Now, if you are down here, you need to add more water. I'm going to write solvents, because this is a universal prep, we'll say. And that's okay. You can add water drop-wise until you get up here. But if you add too much water, wah, 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 wah. If you dilute too much and you go over, you can't remove water, because down here is all your salt, right? Here's all your solute. And as you add water, that solute will percolate up into any space that the solution fills, which means that if you try and take water out of there after you've added it, you're also removing solute. And your concentration won't be what you think it is. It'll be whatever it is with the extra volume that you added. So you cannot add extra water to your solution. If you go over, it's like Price is Right. Oh, damn it. You know, if I had timed this better, I'd thought this through. If you go over, then you have to start the solution over, and you are a big loser. So don't go over, is the story there. All right. Now, interestingly, a lot of people forget this part. When you mix all of these things together, yeah, the salt's going to percolate all through the solution, but that takes a long time. And if you use the solution immediately, because you're not going to want to sit around for an hour for the solution to get thoroughly mixed on its own, don't be ridiculous, right? If you want the solution to be homogeneous, you have to mix it. And so a lot of people forget this part, or they neglect this part. Now, research has actually been shown that this is my symbol for mixing. You stopper the bottle, and then you invert it 50 times. And I'm not kidding. You put your thumb on the lid, you flip it over upside down, you flip it back up. That's one. And so you sit there and you let it mix for a minute. Do, 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 do. I'm actually making the motion. I don't know why. You can't see me doing that. But you just sit there and invert it for about a minute, and when you are done, you will have a homogeneous solution. And people have actually tested this. So what they've done is they have prepared the solution and then immediately withdrawn the sample and tested its concentration, and the standard deviation is ridiculous. Like, all the samples are very different. Then they did it like 10 times, and then they did it 50 times, 100 times, 150 times. And the breaking point was 50. After 50, it's homogeneous. Any extra mixing isn't effective because it's thoroughly mixed. So keep that just factoid in your pocket for when you get into the lab to make solutions, because obviously you want to minimize error. And in order to do that, you have to mix. And 50 times will do it. All right, so that's how you make a solution if the solute is a solid. We're going to talk about a liquid in a little bit here. So what I want you to do is describe to me how you would make this solution as shown. So you want to make 3.50 moles per liter. It's Kbr, and your total solution volume is 1 liter. So first tell me how much Kbr you got to put in the flask, and then describe in words or pictures how to do that. So obviously you can't draw a picture on canvas. That's ridiculous. But how would you describe to me, like in the chat, step 1, what would you do? Step 2, what would you do? Step 3, what would you do? And I realized that we didn't actually indicate the steps over here. So step 1, just hint, hint. Step 1 was to add the solid. Step 2 is to make sure all that solid got in there with water and then fill the line. And then step 3 is to mix it a lot. There is a secret 4th step, which I will tell you after you do this problem. The 4th step actually isn't important. It's just a joke that helps you remember this process. Okay? So make this solution for me. Tell me how much I need. Tell me what to do. I'll give you 3 minutes to do it. All right, one more minute to solve the problem. All right. Of course, we don't capture any of the information because... Okay, that's really all we need for the problem. Okay. I went and looked up the Kbr molar mass on Lentech real quick, so that's what's written down. So I want to figure out the mass that I need to put in there. So that's going to be the molarity times the volume equals moles, and then we'll turn that into a mass. Okay, so let's take my molarity. So I have 3.50 moles of Kbr per liter. I'm going to multiply that by the volume, which is 1 liter. So this would be the number of moles if I hit enter. And I want to turn that into grams, so we'll cancel out moles and turn it into grams. So in a mole, there are 119, grams per mole. And you said 417. That number sounds familiar because I use these problems all the time. So I believe it. Yeah, 416.5. 417 grams Kbr. Okay, so that's how much we're going to use. And then we're going to make our procedure. So step 1 is add 417 grams Kbr to the flask. I'm going to be specific and say what the volume of the flask is. I realize that you guys have never seen a volumetric flask, probably. We're specifically using volumetric flasks so they give you a lot of sig figs. If you just write flask, that's fine. Then we're going to add our solvent, which is water, to rinse and fill to the mark on the flask. And then step 3, mix 50 times. And then there is a secret step 4 that I told you I would share. Enjoy. If you think of making a solution like mixing a beverage or something like that, then it becomes more fun, I guess. I don't know. There you go. Now, in an in-person exam or a test or whatever, I would also allow you to draw a picture. So some people like pictures. And so if you drew these as pictures and drew like a solid with an arrow and wrote 417 grams, and then drew like the little squirt bottle filling it with water, yeah, that's totally fine. Oh, man, what I'd give for a good mojito. That sounds great. All right, now that you know how to do it with solids, let's talk about how you do it with liquids. And yeah, we have like about 10 minutes left. So if you want to make a liquid solution, you really only have one option. And so that option is to turn something concentrated into a more dilute by adding water. It's not as easy to go the other way. And the reason for that is if you want to concentrate a solution, it's sort of like when you're cooking. If you're cooking a sauce and your sauce is thin, you have to heat the hell out of it to get that water out of there so you can thicken it. You reduce it. With solutions, it's the same sort of principle. If you concentrate your solution, you need to remove the solvent. And the only way to really do that is to either let it evaporate away, which is tedious as hell, or to boil it. And we don't really want to be boiling HCl solutions, especially things that are volatile. So, like, your solute could boil away. So, concentrating is not super practical. Dilution, on the other hand, is very practical. You just add water. So, how do you do this? We have a formula. This is called the dilution formula. And it's called the dilution formula because you only use it for dilutions. Dilutions. Okay. Very important. The temptation to use this formula all over the place for stoichiometry in 162 and all sorts of other uses is very high. Don't do it. You only want to use the dilution formula if you are specifically diluting a formula or diluting a solution. If you use it anywhere else, there is a very high risk that you will get the wrong answer, but sometimes it works. And it only works if your ratio of reactants is 1-to-1. Don't use it. Do the stoichiometry in those cases. There is a part in the lab that you have to do this week where it tells you, okay, find the number of moles of sodium hydroxide, and then from that, find the number of moles of HCl. Don't use this formula to do that. It doesn't work. Okay? Do the stoichiometry. Figure out the moles by doing MV equals moles, and then convert moles of NaOH to HCl by doing stoichiometry, which we showed in the lab prompt. You can review that video from Monday to get another idea. Okay. What do these terms all mean? So the side marked 1 is the stock side. And the side marked 2 is the dilute side. Stock just means, hey, that's the stuff that I get from the stock room. This is the solution I'm starting with. It's the more concentrated one. So when you're given a molarity, and it's the bigger of the two molarities in the problem, you're going to use that as the stock solution. M2 will be the diluted solution. Generally speaking, you either select the diluted solution, or it is told to you what it should be. V1 and V2 are just how much of each of those solutions you either take or use. So for the stock solution, you're going to need to put some amount of stock solution in there. So that's going to be V1. For V2, the amount of volume that you want for the entire solution when you're done is what you want to make. Now, in almost every case, we're going to be solving for V1. Because the question that we'll be asking is, oh, I want to make this diluted solution, and I need this much. How much concentrated stuff do I need? And this is the how much right here. Because this number is set. It's printed on the bottle. This number you've chosen, and this number you've chosen. So let's look at an example here. I want to make 0.5 molar calcium chloride. So I'm going to highlight in blue here. This is what I want to make. And I'm going to highlight in yellow. This is what I have. So when you're doing these problems, it's good to do this sort of practice. Like, okay, what do I have and what do I want out of it? Because the have is your stock solution. So this would be my stock. And the what I want would be the dilute. So let's talk about what we should do on this. Oh, look at that. I love it when it captures it correctly. I don't have to do anything. All right, so, oops, hold on. Now, in other texts, you might see this formula written with S and D instead of 1 and 2. Or you might see C for molarity and V for volume or whatever. It all functions the same. They're just variables. We've already decided that this is what I'm going to solve for, so I'm going to just rearrange the equation to do that. And then I'm just going to plug in the numbers like we see them in the problem. Okay. M2, so 2's are the dilute solution. So I want the molarity of the dilute solution that I'm going to construct. You'll notice I'm just going to put M in there, and there's a reason for that. This is how much I want of it. I want 3 liters. And then what's the concentration of the stock solution? It's 10 moles per liter. Oh, look at that. Why write out all those units when they're just going to get canceled anyway, right? So there you go. Now, when I do the calculation, I will get a volume in liters, and that should be... Looks like this is my answer. I did that in my head. If I did it wrong, let me know. Now, here's a question. What if instead I did this? Would this be wrong? Because we've always been doing liters so far, right? What if for some reason I put milliliters in this formula? Well, whatever the units you put in are going to be the units that you get out, right? And so when I do this, instead I would get 1,000 times larger of an answer. And hey, that's exactly the same as this number was in liters, wasn't it? So for the dilution formula, whatever volume units that you use in it are the volume units of the answer. So don't feel obligated to convert everything to liters for the dilution formula. When you're trying to figure out moles and stuff, yeah, you have to convert it to liters, because otherwise you can't cancel out with the bottom part of molarity. But in the dilution formula, if I say I want 400 milliliters of solution, sure, just put 400 milliliters in there. You don't have to spend the time moving the decimal. Because any extra steps that you add could introduce error. If you don't move that decimal enough times, you get the wrong answer. Okay, so we got to put 0.150 liters, or 150 milliliters, of solution into our container. And from that point on, it's exactly the same as what we do for our solid. We have a liquid this time. So step 1, you're going to put in the solution that you measured out. You're going to use some sort of glassware to do this, so a pipette or a graduated cylinder. Then step 2 is you're going to add water. Make sure to rinse this out and this. With liquids, there's much more of a chance that it's going to stick to the sides of the container, so you want to rinse that out real good to make sure you get everything. And then fill it up to the mark with water until it's all the way there. And then step 3, which isn't included on here. That was supposed to be 50 times. Now I'm making you do it 80 times, apparently. I don't know. Oops. 50 times. And then, of course, enjoy. There you go. All right, so now you know how to do it. So I want you to do it for me. So I want you to make 1 molar HCl from 14 molar HCl. And I want 1 liter. And I just realized we're out of time. So, you know what? Let's not do this right now. I'm going to have you do this example when we come back next week on Tuesday, because 2 minutes is not enough to do this. So how many more slides are in chapter 4 here? Or 5, whatever this is, 6. How many more slides do we have? We have 1, 2, 3, 4, 5, 6. Yeah, so we're going to finish chapter 6 on Tuesday. And then we're going to start the horror that is chapter 3. So try some of these problems for practice over this week, because what's going to end up happening next week is you're going to have a chapter 6 quiz, and then you're going to have exam number 1 soon after that. Exam number 1 covers chapters 1, 2, 6, and then a very small amount of chapter 3. Chapter 3 is bad because it's quantum mechanics. It is basically, like, all of this that we've been doing has been more or less what you have done in 140. And so up to this point, everything should have been mostly review. Like, I do mass spec. Nobody else does that. I like mass spec. It was my grad school project. I talk about the history of the atom and all the tests that were done, and that's neat and all, but that's not super like involved. Quantum mechanics is really involved. We are going to talk about extremely nitty-gritty details about electron configuration, which, if you took 140 with me, it's totally new. I don't do any electron config in 140 because there's enough to do. Some instructors talk a little bit about 140 electron config, and it is very detailed, and we move very quickly over a lot of various concepts. And because it's all new, it gets tangled up in your head, and Chapter 3 is where 161 dreams go to die, basically. And if you can make it through Chapter 3, you can make it anywhere in Chem 161. Because Chapters 4 and 5 are not as hard. And there's actually a little bit of review in Chapter 4, because we do Lewis structures again. So, look forward to that next week, I guess. But that's all I got for this week. So, thanks for coming out to the lecture. Make sure that you get quiz number 2 and lab worksheet number 2 done this week, because the due date will be coming up. Quiz number 6, we'll call it. Yeah, electron config is 1s, 2s, 2p, 3, that stuff. That's where we're going. We're going to talk about what that is. We're going to talk about shapes of orbitals. We're going to draw electron configurations, etc. Make sure you get those things in by the due dates. And email me with any questions, or use the Discord. Have a great weekend, and I will see you for week 5.